so welcome everyone. This is the first GeoScan Geophysics webinar. This should take about 45 minutes. I hope I can go through the topics. There are some, I hope, exciting and new information about shallow geophysics during the webinar. And yeah, if you have any questions, just send me an email. I can reply as soon as possible, but I'm gonna just jump right into the presentation. There is a lot to cover, and we are just going to cover a tiny bit of shallow geophysics, if I want to be honest, and it's going to be more of a high-level introduction into geophysics in environmental engineering. So let's start with the first slides, where I'm just going to go into the agenda. Obviously, I'm going to talk about near-surface or shallow geophysics, a bit of geophysics and GeoScan relationship, if I may. I'm going to go into the details of some of the methods that we are offering, and then talk about a bit of the multi-method approach. A few project examples will come up later, and then limitations and misconceptions, because this is a big topic. I hear from clients and from other industry experts even weird misconceptions that are going around, especially in the ground penetrating radar or GPR world, and a bit of the future, which is a bit in the gray area. We don't exactly know what's going to happen. No one really knows, but this is an exciting field for environmental engineering, I think. So there's a lot of possibilities there. About me, my name is Peter Takacs. I have a geophysics degree from 2008. I have about 17 years in geophysics. I started working on the field before I graduated at university, and my expertise is mostly lying near surface geophysics, especially in electromagnetic surveys, which include ground penetrating radar, electromagnetic induction, magnetometry, and all those sorts of various surveys. I'm with GeoScan in the last 7 years, and part of the geophysics department that is a bit a smaller department within GeoScan. So what is near-surface geophysics? I tried to show you a graph that kind of puts shallow geophysics or near-surface geophysics within the geophysics world based on subjective criteria. But I think when you read literature, most people will probably agree on where it stands. So we have geophysics, and the biggest topics or disciplines, I guess, within geophysics is global geophysics. Covers basically the entire Earth. It contains seismology, geomagnetism, tectonism, and even extraterrestrial physics. I give you an example. Right now, there is a tiny rover, not a tiny, but not huge rover on Mars that carries a, I guess, Mars ground penetrating radar. But I think Apollo 17 also had some sort of ground penetrating radar or lunar penetrating radar in the orbiter when they were approaching the moon. I believe the data was not as useful as they expected, but basically the idea is that they could do it, and as technology advanced, they got better and better resolution and more useful data. So geophysics is not constrained into the Earth itself. It's a lot bigger discipline as a whole. The next one is exploration geophysics. Usually we count the first 112 kilometers, 100 meters to 12 kilometers under the subsurface. It contains two main areas, mineral exploration and oil and gas exploration. People tend to put it together. The reason I like to separate them, because oil and gas is such a huge industry that I think it deserves one category itself, because that's where a lot of developments happening. Therefore, it tends to be called like the queen of geophysics, the main thing that is happening in the industry. Everything else is just a sort of like a secondary, if you may. However, it's upcoming. especially the near surface geophysics. I usually go up to the like 50 meters or 100 meters. Some even include the first 150, 200 meters of the subsurface in shallow geophysics. From the environmental engineering perspective, that's actually usually in the last 10, 15 meters. Once the bedrock is hit, usually that's where we stop, or the groundwater a little bit deeper, probably. Within the shallow geophysics world, there are two main categories: environmental geophysics, which I'm going to talk about, and NDT, or non-destructive testing. NDT usually refers to very small scale surveys, concrete inspections, resistivity surveys on different structures, half cell potential that's really used in reinforced concrete inspections, corrosion mapping with high frequency GPR. Those are all part of the geophysics methods or tools applied mostly in non-destructive testing or similar industries. So, what GeoScan and geophysics has, what kind of relationship GeoScan has with geophysics? Well, you probably heard of utility locating. A lot of our clients knows us as a utility locating company, which is true and has been true and will be true. Usually, utility locating goes up to about 3-meter depth, uses high-resolution ground-penetrating radar and electromagnetic method to map out the utilities. This is a very special case of geophysics when accuracy is very important due to future excavations and because the risk that it involves if you are cutting or excavating a pipe, accidentally rupturing a pipe, that can cause serious problems. So the high spatial precision is extremely important, and that's what basically covers the entire utility locating industry to be as accurate as possible. What I like to say is that everything at GeoScan is geophysics because we are using geophysical tools for every single job we are doing. Some say even the drone surveys, remote sensing is part of the geophysics world, and we do carry out remote sensing surveys. Therefore, that's part of the services as well. The geophysics department within GeoScan is a relatively small department, fairly specialized because it is not as well established as utility locating. We have geophysicists and geologists on board. We have 6 team members at the moment, and we have a combined experience of 35 years with various fields, various specialties. We are using GPR, EMERT, magnetometry, and aerial imaging. I'm going to go into the details of those methods and some more in the next few slides. And we are sort of utilizing the multi-method approach, which obviously extremely important because one data set, as you will see through a hopefully very valuable example, is never enough to finish a job or make proper conclusion. So the next one is a few methods. Obviously, when we are talking about methods, there are 2 main areas within the methods from the geophysicist perspective. Those are the passive method and the active methods. So passive methods that are not necessarily generating an external field to influence something in the subsurface and receive some sort of data back that is registered and analyzed. Passive methods are simply measuring a certain quantity that can be plotted usually as a 2-dimensional results or heat map typically in real world. The only passive method that I'm going to talk about is magnetometry. But before we jump into that, we're going to go through a few very cool active methods, starting with ground penetrating radar, or GPR. So how GPR works, it's actually fairly simple. Radar energy is transmitted into the ground, and whenever it encounters some sort of variations in certain electrical properties, namely the dielectric constant or relative permittivity and a bit of the conductivity, some of those transmitted energy will bounce back, kind of received by the receiver signal, receiver antenna, and get registered and analyzed later typically in a cross-section, or what we call it a B scan. An A scan is just one time series that the radar is listening to for a certain period of time. And when I talk about period of time, literally we are talking about nanoseconds. It's a really fast wave, obviously, because it's typically only a third of the light speed in vacuum, what these waves are going through the ground. It has a really high resolution, but it's not good to determine composition, with a few exceptions. For example, metal and voids. Those are typically visible on GPR and data and can be categorized or identified as such. This, the lower image demonstrates one trade-off, very important trade-off that a lot of people kind of forget sometimes, is that you cannot achieve deep signal penetration and high resolution at the same time. There's a trade-off. So if you want to see something big and deep, go for it. That's great. If you want to see something small but deep, that's probably gonna find the physics limitations of that particular project. If you are looking for something underground and you are not sure whether it's even possible to detect with GPR, it's the best to contact us because we can give you an idea. Depends on the soil conditions, depends on the used GPR frequency, and obviously it also depends on what kind of data collection method the practitioner is choosing. A few ground penetrating radar examples I'm going through now. The first one is one of my favorite two-dimensional cross-sections, or GPR profile, or B scan. There are so many words that we are using a GPR word. I'm going to go with a cross-section because technically it is a cross-section of the subsurface. So what you see on the x-axis is the distance from 0 to about 160 in this particular scenario, and the depth is measured in meters. Obviously, those are arbitrary units. You can use feet, you can use kilometers, you can use centimeters, depends on the project. In this case, the given GPR frequency and project objectives give us a meter visualization. If you look at the data, these black and white variations where it gets really amplified, I'm trying to show you with my mouse. I hope you can see these layers that are really strong. Now, those are the interface where the relative permittivity or dielectric constant suddenly changes, either increases or decreases. Depends on the material. Sometimes we can even tell which direction it goes. Actually, it's fairly simple, but it's not obvious most of the time. In complex cross-sections, complex reflection patterns, it gets really, really difficult. But this example obviously shows one of the nicest examples, and that's what I was hoping to show you. You can see the signal penetration is at least 4 meters on this particular cross-section. On the left side, you can see how it's nicely, the variations still come up around 4 meters below ground level. The next example is how we analyze the signal. On the right top corner, you see a GPR cross-sections, and on the left side you see the combined cross-sections into a 3-dimensional volume. Essentially what you see on the left side is a map view. Imagine that you collect a lot of GPR lines next to each other, parallel lines next to each other, sometimes a little bit in an angle, and then you plot everything into a map and you try to see the variations from the top. and then you change the depth slices. What we call this is basically slicing the data set. This is exactly what we did. We sliced the subsurface based on the relative permittivity variations. That's what you see on the left side. So the technical term of what you actually see, what that heat map is representing, is a GPR reflectivity. So where it's strong, there is some sort of feature that reflected back a certain amount of energy. As you can see, there's a linear feature there. The red is actually representing the cross sections. So basically the 0 meter is at this little green dot at the top right there. And the end, which is around 22 meters, is somewhere here. Because this is a GPS-based survey, we can actually map out every variations using a high precision GPS and then plot everything in GIS. Now I'm going to demonstrate in the next slides how we do the analysis. So I'm going to start. This is going to be a short video just to give you a sense of how we analyze a signal. Both the cross-section and the map view is technically a processed data set. So I'm not going to go through the processing. I'm just going to show you how we do things. So first we see this map view. And then in the map view, we can change the depth using the cursor on the cross-section. And then we change the depth accordingly. And as we change the depth, we see several features. In this case, we see a linear feature and a lot of other features that I'm going to point out, at least one of them. Once I find a feature, I add an annotation on the map. This is exactly what I'm doing. The linear feature will be most likely a utility, so I'm going to call it a utility. And I try to be as accurate as possible. Obviously, the depth is recorded, so every feature that we mark will have a depth associated to it. Once the utility is marked, I'm going to go through. I'm just going to point out one more. You see that weird looking feature, like black areas around the white ones. The bigger context here is that something is next to a utility and we may want to mark that. So I'm zooming in the map and kind of find it in the cross section, the exact same variations. And I find this amplification, this stronger black and white sort of signal, which means that there is an extra energy that comes back from that interface. So I'm going to mark it out. In this case, I call it an unknown feature because I'm not 100% sure what the source of this particular feature is, but I can come back later. Maybe I have a better idea once I plot everything on the map, or maybe the client knows something about it. Maybe it's a buried tank. Maybe there used to be a small building and this is a remnant or debris. Or it could be as simple as just increased water content because of a ruptured pipe. Sometimes that's what's happening. So this is just an example process of how we analyze the data. So electromagnetic induction is our next method, or EM, which I usually call it the cousin of GPR. This is not an actual term. This is a very subjective way to look at it, but it uses varying electromagnetic film from a transmitter coil, which generates this primary variable magnetic field. And since Maxwell, we know that these changing primary fields will generate eddy currents in any conductive material, which is basically the subsurface. Sometimes it's a lot less, sometimes a lot more, depending on the conductivity of the material. And this changing eddy currents also going to generate a secondary magnetic field, which is also varying in time, that is received by the receiver coil and kind of compared to the primary field. Also, it is basically divided into several sections, several parts, namely the quadrature and the in-phase part. It's basically every registered field comprised of these two parts, if you may, the quadrature and the in phase. The quadrature is basically a 90-degree shifted signal compared to the primary field. The in phase is in the same phase, hence it's called the in phase. So typically the quadrature is considered at the conductivity of the subsurface, or if you have superficial features, obviously we're going to see that as well. And the in phase typically related to the magnetic susceptibility. So metallic content is going to show up because they tend to have high magnetic susceptibility. A few electromagnetic examples. Electromagnetic method doesn't produce per se cross-section. It is producing sort of like 2D geophysical results plotted as a heat map over an area. This is what you see. There are two data sets that I show right now. And the most obvious thing that you can see is that geophysicists love rainbow color. This may not be the most appropriate visualization sometime, but the reason why we like that, at least I like it, because it shows variations. And most of the time, this is what's important. Most of the time, the quantity, the metric that we measure is not as accurate as we would like to because of the calibration issues, because we have limitations. So we are focusing on the changes of these metrics, and this is what's important. If you have a background conductivity, for example, of 10 millisiemens per meter, and all of a sudden you see an area where it raises up to 50 millisiemens per meter and you can kind of cover it, you can probably have a good idea that there is some sort of additional phenomena going on right there. For example, maybe you have some extra contamination in the ground of water, some sort. This is exactly what, by the way, these areas shows. On the right side, it's really clear. It was like it was surveyed in a yard with a few salt sheds present, and those very high conductive zones that are showed as a red areas. Those were very close to the salt shed, and most likely indicated higher contamination, higher salt content in the groundwater, and obviously those will follow the general groundwater flow. That's why it goes into like one general direction, because it's going to follow the groundwater. Technically, when geophysical surveys, geophysical methods are used for contamination, we don't technically survey contaminants or contamination, or what we measure is the background conductivity due to the groundwater or increased groundwater conductivity. That's a really important details to share. And sometimes people forget that we can see contamination, and we can even give some sort of quantifiable data of what kind of compounds that might be, which is not true. What we simply can do is map out where basically the groundwater has increased conductivity. The next method is electrical resistivity tomography, of ERT, and now it's kind of similar to the electromagnetic method. It's going to give a cross-section. However, although a three-dimensional ERT survey can give you all kinds of visualization, even in a map format, obviously. But we are focusing on the two-dimensional ERT surveys, in which case you have a survey line with a lot of electrodes inserted into the ground, a few inches, and then we pass through a DC current into the ground through certain electrodes. In a single channel mode, we are using 2 current electrodes and 2 voltage electrodes, where we measure the potential differences, and using some relatively simple calculations, we can calculate the operant resistivity at every single point for every single electrode combinations. Once we calculated the operant resistivity through geophysical inversion, we can estimate the resistivity distribution along the survey line. So how it looks like? It looks like this. Essentially, somewhat similar to GPR, although again, a rainbow color scheme is used because we love seeing variations and where the big changes happen. And this is what you can see. Obviously, the purple is a very homogeneous material. In this case, the visualization let you show that the purple area has higher resistivity or decreased conductivity. You see, I use it, and everyone else, I guess, is using it interchangeably. Conductivity and resistivity waves are just reciprocal of each other. And on the top, you see a lot of variations. Typically near the subsurface, near the surface, very shallow, the first few meters, you will see a lot noisier data. Electrodes are close to each other. There's a lot going on. The water content might be really different. There might be bigger rocks and near the surface that might be introduce some additional noise. Also, all kinds of electrical noise can alter the nice readings, especially near the very top. Another example is the lower part of this graph, where basically you see the same thing with slightly different color scheme, where we wanted to emphasize high conductive areas. We changed the visualization, so the blue in this case means low conductivity or higher resistivity, and the red means higher conductivity. Essentially, the visualization can be tailored for every project. So again, I wouldn't emphasize too much about what color scheme is used because it's not standard. But what's important in this case is that if you do an electromagnetic survey, which can be done fairly quickly of very large areas, you might actually miss deeper targets because electromagnetic methods have a very limited signal penetration compared to ERT. ERT has obviously limitations, but even in these little examples, you can see that we could see at least 10 meters below ground level. With the electromagnetic method, depends on obviously the antenna you are using, but typically what you can achieve right now is about 5 meters with the typical instrumentations people use, which might be enough for environmental engineering applications, but sometimes you need a little deeper penetration in order to find the root cause of increased conductivity even. The next method is the only passive method that I'm going to talk about during this webinar, which is magnetometry. Simply, it measures the Earth's magnetic field and it plots or registers variations in a small or larger scale. It helps detecting composition. Obviously, it's very sensitive to magnetic materials and minerals. Therefore, we have to be careful even when we are wearing the instrument to make sure that we are completely demagnetized, which can be sometimes a challenge, but we have to make sure that we are completely free. Otherwise, due to the sensitivity of the instrument, it's going to be a completely useless survey. It is mostly used in archaeological surveys, some shallow geological surveys. Volcanic rocks, for example, the volcanic rocks delineation is one of the examples where we can use this particular method. But again, it's very sensitive. Typically, we use gradiometer, which is one type of magnetometry when you are collecting two readings at a certain distance from each other and use the differences between the two in order to plot a radiometry map of an area. The reason why this is helpful, because the Earth's magnetic field changes even during the day. So you can kind of eliminate all the corrections that needed in order to properly create a surface, an anomaly map, magnetic anomaly map. Gradiometers helps to eliminate those needs. An example data set is, this is one of those methods where we use a grayscale. You see these black and white variations. Those are what we call it the dipole type anomalies. They are usually referring to some sort of strong metallic objects. But what we're really interested in these cases is the context. If you plot the interpretation, the preliminary interpretation on this, you see some sort of variations. This actually turned out to be a building outline. We have GPR data sets from the same area, and we kind of see the same variations. And then we got information that indeed there was a building there before. The last method I'm going to talk about is shallow seismic, which we currently do not offer, but it's in the plans for the near future, and it's also very important in shallow geophysical investigations. Shallow seismic or seismic, the reason why I want to emphasize is shallow seismic because a deep seismic typically used in oil and gas industry, and although the theory is very similar, they are usually a 3D large-scale surveys, a lot more logistics involved in their field operation. So seismic uses acoustic or mechanical energy, usually generated by, in our case, either a hammer or a small scale, some sort of vibrating mechanism. And these acoustic energy or waves traveling through the surface and reflections, refractions will come back from interfaces of different density materials, where the seismic wave velocity changes enough. In that sense, it's very similar than GPR, especially the data processing. Geophones usually put on the surface in a survey line, and they are registering those incoming waveforms. You see there is a lot of different ones, starting from air waves, direct waves, reflected, refracted waves. And the job of the geophysicist is to make sense of these chaotic incoming signals. It is used for measuring mechanical properties, obviously, most importantly, stiffness or density. And I'm going to show you two example data set. This is very similar to a GPR data set. How you look like? You see layers that are basically showing variations in the seismic velocities. In the case of GPR, same thing. It basically shows the variations in GPR signal velocity, and the velocity changes happen when you have different dielectric constant of the materials. In seismic, it's usually the density that governs the velocity. This is a huge data set. What you see on the left side is similar to the GPR earlier. It's the depth axis, and the horizontal one is the x, is the distance. And you can see the scale is about kilometers, so we can see about 15-20 kilometers section by about 3 kilometers in depth. This is the fault zone, lovely, from USGS. I highly recommend their site, by the way, for all kinds of geological applications. The last example for seismic is MASW. MASW stands for multispectral analysis of surface waves. Essentially, it's used for shallow investigations, most importantly for bedrock mapping and shear wave velocity calculations. It's typically used in the last 10, 15, 30 meters, depending on the project. And the example shows essentially an MASW cross section. The red part in the heat wave, another color scheme, another rainbow color scheme visualization, is where the stiffness is the highest, where the geophysicist interpreted as bedrock. You can see on the right and the left side of this graph is probably a weathered bedrock where you don't have that clear homogeneous response. And the blue areas where the stiffness is the least, that's probably the overburden, the soil, and the shallow deposits. A few other examples for different methods are self-potential, induced polarization, gravity, radiometric, or borehole geophysics. The examples here just showing a lot of rainbow-colored examples. This is just to show that there is a lot of possibilities in shallow geophysics, and not all of them are used in engineering applications, but there are always studies which one can be used for certain applications. So the future in that case is, I think, really exciting, because there will be probably new applications that are coming up in the next few decades. Now, the multi-method approach is what it is. So when a client comes to us with a certain particular questions about how to find certain objects, features, or just verify a few things underground, we typically suggest one main method and the secondary method. And the reason behind is going to be demonstrated by a nice parable of the blind man and the elephant. Essentially what happens is a few men who had never seen an elephant before were asked to describe how an elephant looks like just by touching it. Obviously their eyes were blinded, so they couldn't see, but they could touch it. And they all described what they could feel really well. But as much as they were correct, all together were obviously wrong, because they used their limited experience and knowledge of an elephant that they had never seen before, and they gave over the wrong answer. This is true for geophysics, geophysical surveys as well. If you are using one method that is sensitive only a limited number of parameters, you're going to get a very limited answer. Even if you use 2 or 3 methods, sometimes the answer will be ambiguous. This is something inherently true for every geophysical survey, but you have a higher chance to have a better object or target or feature identification. And this is what's important. Every single additional method increases the chance to get a more accurate answer. So since it can help clients better understanding what's going on, and us better understanding what the context is and what kind of features we see on one data set, we always use at least 2 methods plus drone imager that also help understanding what is going on. A few examples for multi-method geophysics, where we use remote sensing, area photos or historical photos, as well as borehole information, if any available. Obviously, everything has to have direct sampling, either from one of the used methods, either GPR, electromagnetic, ERT, magnetometry, seismic, or whatever we are using at that point. We like to correlate those survey methods and visualize them simultaneously, because this is when everything comes together and creates a more sensible results. A few examples how they can be combined and why they help each other, basically. GPR and ERT examples. You've seen these both separately before. Now they are together because they were collected on the same survey line with different depths. I adjusted their visualization to match the scales of the X and Y axis. This was a bedrock survey for initial site characterization. It was a forested area, difficult terrain to work with. We had to walk through both the GPR and the ERT electrodes and survey lines across the forest. Sometimes it's difficult to find even proper ground when you have a dense, especially here in the Pacific coast. Find the actual ground in the vegetation. So when you put this together, they clearly line up very nicely, follow the same bedrock surface that we interpreted as bedrock. On the GPR, you see a nice interface, and we were very sure that it's the bedrock surface that we could see, but the ERT finalized our interpretation because it gave us actual quantifiable data in terms of its resistivity, which was really high. There's a purple area down that you can see clearly, and then we could identify it as bedrock. The next example is when we use GPR and EM together. In this particular scenario, it was a relatively simple task, if you may, which is never true. It was a USC locating example, and GPR would be the first choice. I say, oh yeah, definitely use GPR right from get-go. However, in this case, it was a large parking lot, so GPR wasn't really feasible. EM, however, is a lot faster, and unless it's really complex subsurface, EM will probably give you a better idea of where to look, where to concentrate the GPR survey, and this is exactly what happened. So we focused on a large area using an EM survey. We quickly got it done, and we analyzed the results on site, and we found a clear anomaly where we then, the same day, did a relatively small scale GPR survey to make sure that it is what we think it is. And this is what we found. We found the depth and the exact geometry of that target that the EM picked up. So it wasn't a superficial influence. It was indeed something underground. If you look closer, by the way, you see that on this little snippet of the GPR analysis software, the top shows the map view and the lower part shows the cross-sectional view. It's just different than previously. And in the cross-sectional view, you see that a really strong black and white, like two hyperbola next to each other sort of look is visible. While on top of it, you can see some sort of, not U-shaped, but almost like a wide V-shaped layer, which we think is from the original excavation. And this is one of the beautiful things about GPR, that it can actually see unexpected results or changes in the subsurface, even probably after decades when they happen. I'm going to go through a few project examples. I promise it's not going to be too long, but I think they are really important to kind of tie everything together into into a few nice projects. So sometimes we are told that they are just expensive toys and we're just walking around, which is kind of true. They are expensive. We are loving them, and we love walking around because they introduce really cool results when we finally analyze the data. But geophysical techniques are typically used for, and I'm just gonna give a few examples. Highway inspections, for example, asphalt thickness, road base thickness, and variations. Ray avail, most importantly for ballast inspection. This is mostly GPR, but resistivity surveys also used for ballast inspection, even void detection in train lines, depending on where it's located. Contamination mapping, which is technically the groundwater conductivity mapping, not contamination, but the results are basically the same. buried waste mapping, metallic and non-metallic. This is used mostly GPR, used for those kind of projects. Immediate hazards, meaning sinkholes usually, and deformed stratigraphic units. That's for geotechnical work. It's not always feasible to do the geophysical surveys because by the time it gets to the point where it becomes hazardous, the data collection may not be safe. So this is something that is also part of the limitations. The last one is archaeological sites. It's not just with GPR, but with magnetometry and electromagnetic as well, either preliminary inspections or narrowing down archaeological sites. There will be two examples. Example number one is a single method, so our interpretation was limited. We use electromagnetic method, two types of electromagnetic methods. So we had some depth information, excuse me, and we were looking for buried foundations, pipes, anything that's metallic and large. So this is exactly what you see on the picture. You see the hedged areas, those are the obstructions or existing features such as buildings or known foundations or obstructions like debris on the surface or stored material. Everything that's outside and sort of black area, those are electromagnetic features, geophysical features that we marked out. I hope you can see my mouse and you can see where I point. That one is, for example, a foundation, building remnants that were not previously known, but there's another foundation next to it and a little bit north of that. There are other anomalies that were noted, like pipes and localized anomalies that were interpreted as metallic objects or buried objects that changed the soil conditions significantly. Maybe they were excavated and then buried, something buried there. In this particular case, a lot of features were noted, and the client needed that information because I think they did some serious development on this industrial site. The next example is an old salt storage area. What you see is the electromagnetic survey results. Red indicates higher conductivity and the blue indicates the background conductivity essentially. And the background image is a little bit older Google image where you can see there are two salt storage area, salt sheds next to each other. One was completely demolished. The other one was demolished as well, but something was stored on top of it, on the top of the location. So we couldn't complete the scan entirely. That's why you have some areas missing data. Obviously, there were some concerns that the contamination from those salt sheds leached into the groundwater, and the groundwater carried away from the original area down to the nearby fields, which is located south of the area. Those dashed red lines indicate electrical resistivity tomography or ERT survey lines. Those survey lines were planned after we did the electromagnetic survey and we processed the data, plotted the data on the map, and kind of planned where we need to get the ERT line completed. Strategically, we wanted to go through the highest conductivity area because we wanted to catch that, if you may, and then we went to the field nearby, the field in question, to make sure there is nothing that we can see of higher conductivity. However, as expected, ERT showed a bit more. On the left side, you see two cross sections, above one another. The first one was directly going through the salt shed that was completely demolished. And if you see this red area, this is exactly where the salt shed used to be. If we go back to the previous slide, this is the ERT line I'm talking about. And this is the higher increased conductivity that you can see on this new slide. Same thing kind of happens on the other one, which is parallel to the first one. It was located right here. I'm trying to show you where it's located. And then if we go back, you see the higher conductivity is at the beginning of the line, and then kind of changes near the top. However, if you take a closer look, something happens at the deeper level, as if the conductivity increased at around 5 meters. I need to check the scale, to be honest, because I can't really read it. It's not high enough resolution from the screenshot, and I don't remember the exact numbers. Now, the right side is the two parallel lines in the field, which are this and this one. And if you go back, you can see that the top few meters are very homogeneous, exactly what we got from the electromagnetic survey. But something happens a little bit deeper, and this is where drilling will help after we completed the geophysical survey. We discovered that at certain depth, the conductivity significantly increased even in the field up to essentially almost at the entire cross-section, especially at the beginning here. So this is one of the examples when a single method, an electromagnetic method, would have said that there seems to be no influence from this higher conductive area to the nearby field. However, when you see the electrical resistivity tomography survey results, or ERT results, this image is a little bit more complex, because there are increased resistivity, increased conductivity areas after a few meters below ground, which might indicate that something else is happening. Now, whether this is just the groundwater flow or increased conductivity based because of the increased salt content, that's something an engineering firm can confirm based on targeted boreholes. The next thing will be a few limitations and misconceptions that are usually related to geophysics, especially with the GPR. One of them is that geophysics is art. However, it's indeed based on scientific principles, although the unknown variables create this inherent ambiguity, especially in the data interpretation. We can't see into the ground, but we can see changes of certain properties of the ground that we have to interpret. And that's the most difficult part in every geophysical project. Another misconception is that geophysics sees everything or geophysics doesn't work. Either one of them. Sometimes I hear one, sometimes the other one. Now that it sees everything, that's obviously not correct. I just mentioned that it only sees variations of certain physical properties, which is true for every geophysical survey. The other extreme is that it doesn't work. I always say, well, if you look at the oil and gas industry, it's doing pretty well, and it's mostly based on geophysical surveys and borehole locations, obviously, but those are usually based on geophysical surveys. Geophysics works if you take into account the limitations and if you understand the ambiguity in the process. It's usually just one piece of the puzzle, and it won't solve every problem, unfortunately. Sometimes it can pinpoint, however, where you have to look for certain things, For example, metallic debris or UST or conductivity surveys are one of the examples where things fairly straightforward. Also, one method doesn't rule them all. There is no one single method that can solve the problem for everyone. That's why we need to apply the multi-method approach. I ran the equipment, and because it looks easy, this is sometimes I get from clients, and they're really happy to help with equipment rental and to anyone who wants to learn more about it or conducting the surveys themselves. However, they have to understand that there's a lot of years going into every single project preparation and planning, because the underlying physics needs to be understood in order to get the most out of every single data collection. And that can be really tricky. And even when we think we get everything right, we still have issues sometimes with the conditions, unexpected conditions. A few limitations. Just gonna mention maybe one for every mentioned method. GPR, the conductivity is one of the biggest issue, and the resolution decrease over depth. High conductive areas will not work for GPR, especially clay-rich conditions. In terms of electromagnetic methods, kind of the same applies, but also superficial interferences can be problematic. So if you have an area that needs an electromagnetic sweep, it needs to be cleared in order to get proper results. In terms of ERT, it's basically usually just the data collection, what is the problem that causes problem. It's relatively slow, especially compared to EM and GPR, but usually it provides really, really good results. Magnetometry, usually sensitivity, that's the only thing that I can put out. And because of the sensitivity, it picks up a lot of things. So it's usually not used for environmental applications, because you don't need to see every little metallic object, but you need to see a larger context of a site usually. In terms of seismic, it's excuse me, its resolution is usually dependent on the size of the anomaly, and in terms of the in case of the refraction, it's refraction works if the velocity increases with depth. That's how the waves can basically travel at the interface of the two different layers. So the last thing I want to mention is the future and what's ahead. And I mentioned before that it's a bit gray, mostly because we don't know what's going to happen and how the surveys will improve in terms of accuracy, object identification, or even how physics will change, to be frank, because it hasn't really changed in the last, I don't know, 50, 60 years, but the advancements really happened in visualization, in technology, in resolution, data resolution, and data collection speed. Those are really increased in the last few decades. The next big thing, obviously, everyone's talking about are aerial and drone surveys and AI-backed interpretation. Now, those are kind of not necessarily the present yet, but we have already experimented with different drone surveys, and for certain type of geophysical surveys, drone surveys work really well. For others, like GPR, we have not yet been able to get good data. So we are putting that aside for now and waiting for the industry to catch up, because we believe that we just want to get the best data available at the moment to collect the best quality data. So we may have to wait for proper drone surveys in terms of GPR, but for other methods, it's kind of working for large scale variations. So if you want to get a magnetic survey done from drone, it's possible, but there are certain limitations you need to understand. For example, it's going to be a really low resolution, and it has lots of caveats otherwise as well. Interpretation-wise, there are already works and researches into AI interpretation in geophysics, which would probably help geophysicists to better identify certain features. However, in shallow geophysics world, the problem is sometimes the lack of data that can be fed to the model, that AI model that will return help the interpretation in the long run. So, as this is my personal opinion, that probably lack of data is what's causing this sort of slowdown in the geophysical interpretation. However, for example, in seismic oil and gas industry, probably there is a lot more. So I think we're gonna follow them sort of in a few years. What they are doing, we cannot most likely reproduce once we have enough data to justify it and to feed the models. Well, thank you for your participation. I hope you enjoyed it. Sorry, I tried to compress it within 1 hour. That didn't really work, but I hope you enjoyed it, and I hope you learned something new.